Hi, everybody. My name is Snigdha Sarkar. I am the Senior CFD Application Engineer here at KETIV, and I welcome everybody to today's KVA session. So today we're going to be talking about Fluent Expressions and how we can use them conveniently to customize our setup and get more out of our CFD simulations. So for today's agenda, we're going to start with the motivation of why we need Fluent Expressions. Then I'll talk a little bit about how it can be used in your CFD setup. Some syntax basics that will allow you to follow along when I actually demonstrate how to assign these expressions later on in the KVA session. And then the different ways of entering expressions. I'll talk about the differences a little bit. And then I'll do an example problem wherein I'll assign a couple of different expressions in the Fluent window. Hopefully all of this helps you to get started with using expressions for your own problem. At the end of the session, we can take any questions that you guys have regarding the content that I present. You can see a Q&A box on your screen. So if you have any questions, feel free to drop the questions in there. Okay. So with that, let's get started. Now, why do we need Fluent Expressions? Why are we talking about it, right? So for those of you who are not familiar with using expressions, let me just briefly define them. They are uniform and non-uniform function of spatial coordinates, time, iteration, solution variables, different physical constants, and perhaps profiles that you want to assign in your CFD setup. They're simple and intuitive to use. They're just like mathematical expressions. So even if you're new to the concept of expressions, it'll be pretty easy for you to get up to speed on it. This is much more convenient than using the more traditional approach of using user-defined functions or UDFs, as a lot of us CFD users know. Those are written in the C programming language. And if you're not very familiar with the C programming language, then it becomes a whole lot of effort to understand how to write UDFs, how to interpret the different macros or different variables that go into writing simple functions for assigning complex boundary conditions and settings. So instead of doing all that, we can use expressions. It becomes much simpler to customize settings for your problem. So let me show you an example over here. This is just a converging diverging passage. Suppose we have to assign a time-varying sinusoidal pressure profile at the outlet boundary. This is how the pressure will be varying with time. You can see over here, you have an operating pressure component, and then you have some periodicity in this sinusoidal function, wherein you have the frequency to be around 350 hertz. If you were not using expressions and you were assigning this boundary condition in the traditional way, you would use a UDF. This is what the UDF looks like. And if you have no background of coding, or if you don't understand C programming language, it might be difficult for you to interpret it, right? What is defined profile? Is that a predefined macro? What type of variables do I use? Okay, now I have to convert it into an SI unit variable. I can see that there's some sort of loop in this function. What is this, loop doing? So there are so many things to understand in this UDF, it becomes quite complicated. But if you were to use expressions, and I've included a snapshot of the GUI for doing this type of a problem here, you can see that the simple mathematical expression can be entered in the Fluent window itself without you having to use a text editor or compiler or worry about writing a UDF function. You can simply write the expression over here and then assign this expression as the boundary condition at the outlet location. So this is much more intuitive, and even people who have no experience with coding can come up with this type of expression quite easily. Now, we talked about why we need expressions, but where all can we use them, right? So the previous example showed how you can use expressions for boundary conditions, but they can also be used for assigning source terms, different material properties. And then if you want derived variables for post-processing to gain extra insight from the results of your CFD simulation, that can be done as well. Expressions can also be used for printing out reports. So whatever expressions you have set up in your CFD setup, they can be included in the reports. They can be reused even by exporting them into a CSV format. Now, a little bit about the Fluent expression syntax so that it's easier for you to follow along when I write the expressions later on in the demonstration. Basically, these expressions are combinations of values, variables, different mathematical operators, and functions written in the Python syntax. Now, don't let the word Python scare you, because even if you're not well versed with Python, you can write these expressions quite easily. If you do it 1 or 2 times, you'll know how to sort of use the right operators, right brackets, how to assign the units, variables, etc. Fluent expressions are case sensitive, so keep that in mind. All types of values can be included, real numbers and integers, even Booleans like true or false. And when you're assigning quantities, you will obviously assign the magnitude, the real number that is associated with the quantity, but then the unit becomes very important as well. Units are usually enclosed within square brackets. So you can see over here, suppose I wanted to assign this number as the mass flow rate, kilogram per second, then I would have to assign this unit to tell Fluent what quantity this is, okay? Now, the other important thing about expressions is that they can either be single valued or they could return a range of values in a field. If you look at these 3 expressions over here, the first 2 expressions are for calculating the velocity at the inlet, or velocity at any flow boundary, doesn't really matter. If you look at the mathematical expression, the first one is varying with time. So T stands for time. T is a variable for time, right? And you can see that for every time step, this expression is going to return 1 single value. Okay, it's going to be 1 constant value for every time step. Similarly, in the second expression, the area of the inlet is constant, depending on how you've set up the domain. So again, this expression is going to return 1 single value. These were velocities. What if you're talking about heat source? Okay, so in this particular expression, it's either going to be 10 watts total user volume, user heat source, or it's going to be 0 watt per meter cube Kelvin, either of these 2, depending on whether the condition is met, okay? But at any given point, it's going to be either 10 or 0. So again, it is single valued. Now, what if your expression was varying with spatial coordinates? Say, for example, here, the velocity has some function in which you are taking into account the radius of the flow boundary. Now, the radius at every point is different. Why? Because the coordinates are different. So at every point, x, y, z is different depending on how you've built the mesh. So this expression is not just returning you 1 single value, it's returning an entire field, something that you can plot as a contour once your simulation has completed. Okay, so the distinction is important because in Fluent, some input variables will only accept single valued expressions. So if you try to, enter a multi-valued expression over there, it's going to give you an error. So that is another distinction that you need to keep in mind. The other thing about expressions is that sometimes they need extra context. You may want to print out the mass fraction of a particular species in your CFD simulation, but unless you tell Fluent, okay, which species are you talking about or which phase you're talking about, you're not going to be able to get the right answers, okay? Now, this is just, a slide for the different units for most of the frequently used variables. You can see that these are not just restricted to SI units. You can use all different types of units. Fluent eventually converts everything to SI if that is what you've selected in your setup. But I just thought if somebody wanted to pause and look at the units later on, this might be a helpful slide. The thing about units is you need to keep in mind the general format for how you assign them. So I already mentioned that they go in square brackets. Usually there'll be a multiplier. Say, for example, you want to look at nanometers. So, you would put an N before M just to make sure that the multiplier is there. And then, it'll usually be raised to some power depending on which variable is intended for assignment, right? So say, for example, if you're doing meter per second, then, second can be raised to -1 because it goes in the denominator. And so you can raise it to the power with the help of this caret symbol over here. Now, the other thing about units is usually when you have a multi-string unit with variables, multiple dimensions in the same unit, then make sure that you put a space in between the different individual units over here. So you can see there's a space between kilogram and per meter, and then per meter and per second. So that's how you can differentiate between different dimensions and multipliers. All right. The thing about units is they need to be consistent. I'll talk about it in detail in the following slides. But suppose you want to enter an expression for the velocity at a boundary, then make sure that at the end of the expression, the value that is returned has the same unit as the velocity field that it is going to. So if it comes out to be meters squared per second instead of meter per second, then Fluent is going to give you an error. So you can see an example over here, okay? Here we are dividing feet cubed per minute by area. Now, directly, you're not assigning meters squared per second or feet squared per minute. But what happens is because there is this division function over here, if you look at the dimensional consistency between left-hand side and right-hand side, your left-hand side is velocity, so it is L1t minus 1. And then on the other hand, you are dividing feet cubed per minute by area, so it again boils down to the same dimension. So this consistency needs to be maintained, otherwise Fluent is going to give you an error. All right. So here's a snapshot that shows you what type of error you can expect. Fluent was expecting kilogram per meter cube per second in this field, but we entered kilogram per second, so it immediately gives you an error. You enter the right units, and that's going to work just fine. Now, how can we assign expressions, right? Is there just a single way of doing that? Well, no. You can assign the expressions directly in the field, directly where you assign the boundary conditions for a particular flow boundary or a cell zone. So over here, we are assigning some velocity at the inlet, and you can actually type out the mathematical expression in the GUI itself. You don't need to go anywhere else. But alternatively, what you can also do is you can use the named expressions or expression editor in the outline view, and then that gives you some additional functionality because you're writing the same expression over here. But as you can see from the snapshot, you also have a context menu right next to it. And this allows you to drop down, say, for example, functions, variables, constants, and look at all the options that are available to you. So if you're starting off with expressions, I would say this would be the better way because it'll tell you a lot more things than just directly assigning the expression in the boundary condition box. Now, what additional things can we know from using the expression editor? So this is like a full snapshot of the expression editor. It shows you one of the context menus over here. Say, for example, you want to find the average temperature at the outlet, okay? So if you click on functions, it's going to give you all the functions, all the averaging functions that are available to you for using. This is very similar to using an averaging function from report definition. Those of you who are familiar with Ansys Fluent, we do that quite often, right? Once our simulation is complete, we'll go to report definition. We'll either look at area weighted average or mass weighted average of different variables. Same functions available to you in the expression box as well. So you can look at the list of all mathematical functions, conditional statements, everything that you want to use using the expression editor. It also allows you to look at the syntax in a more comprehensive manner. You can do a couple of more things with the expression editor. So over here, if you see, while you're writing the expression, if the expression is not complete, or if the expression has incorrect syntax, you can usually tell by the indication of this red box, or there will be a message that says incomplete expression over here. So this is only in the expression editor. This is not shown to you or known to you if you start writing your expressions directly in the boundary condition box. Okay. The other thing is, say, for example, you have initialized your case, right? So there is some data available at every cell. Now, if you've written an expression and you want to calculate its current value, say at the initialized stage, or maybe after a particular run, like, it has some time has lapsed at some particular time step, you want to look at the value of an expression, you could also go ahead and do that. If you click the green button, it's going to return the current value of the expression based on what you've assigned it. Okay. Now, again, this is only for single valued expressions, right? So if your expression is varying with spatial coordinates, then it cannot give you an entire field. But if it is a single valued expression, you should be able to compute it in the editor. The other things that you can do with the expression editor is, once you've entered an expression and you've set up your case, say, for example, you have a function that you've assigned to some boundary, it's going to tell you where all this expression is being used. So one look at the editor and you can tell, okay, I'm using this expression over here, I'm using this expression over here. You can also assign these expressions as input and output parameters in Workbench. And that is very convenient. Say, for example, in this expression, we want to do several design iterations by varying the value of omega. Now, if you set omega up as an input parameter, or if you set up this entire expression as an input parameter, you only need to check this box, and then you can enter the different design points in Workbench and update the various design points through the Design Explorer. So using these expressions as input and output parameters is also possible. The other thing that I find quite handy is, sometimes when you are assigning mathematical expressions, you want to look at them in the form of a graph, just as a gut check to understand that you've assigned it correctly. Okay, so say, for example, this is a sinusoidal function. You want to make sure that you've assigned this correctly, right? Your expression is right. So you also have the option inside the expression editor to assign a minimum and maximum value. And based on the mathematical function you've entered, it's going to plot it for you. So this could be a good gut check to make sure that you've assigned things correctly. Okay. All right. So we talked about some basics for assigning expressions using our slides. Let's do an example problem wherein I actually show you how to assign these expressions. What we're going to do is we're going to take a simple pipe flow problem, and we are going to assign a turbulent velocity profile at the inlet. The function of it looks like this. So Umax will be a value that I assign, and the maximum radius will be a value that I assign. This radius will be computed based on the coordinate location or the spatial coordinates at the particular flow boundary. Okay, so we'll assign the turbulent velocity profile at the inlet. We'll also assign a transient pressure at the outlet, right? A pressure condition that varies with time. We'll also use an expression to assign a volumetric heat source in one of the fluid volumes in our domain. And then we'll use some expressions for post-processing. So I think if we do all these things successfully, it'll give you a good comprehensive idea of where all you can use expressions in your own problem. Okay, so let me go ahead and show you the geometry. So you should be seeing my Fluent window on your screens now. Okay. This is a simple example pipe. I didn't check the dimensions. I just, built something arbitrarily. And I've loaded this in Workbench. I've already opened the file to save us some time. The mesh is quite coarse again, because I don't want to spend too much time with the computations. But basically, one of these zones is going to act as a heat source. There is an inlet on one end and an outlet on one end. Okay. So the first thing I'm going to do is I'm going to assign this as a transient case, because remember, we were going to vary the pressure at the outlet with time. Okay. So let me go ahead and do that. I'll also go ahead and assign the units for temperature as Celsius. Okay. And then I'm going to go ahead and turn on the energy, because I can't assign a heat source if the energy equation is not turned on. Okay. Now, I generated a default mesh in Fluent Meshing without actually opening it. So everything is by default considered a solid. So let me go ahead and make all the domains fluid domains. Okay. So this particular domain is going to be my heat source zone. Okay, so I'm going to assign a user heat source for this particular domain using an expression. And for this, I'm not going to use the expression editor. I just want to demonstrate an example where you can directly enter the expression in the field itself. The material is air. I don't want to, bother changing it. Let me just go ahead and assign a source term over here. So this tab becomes active. And we can come to the energy field, click on edit, increase the number of energy source to 1. And then it is asking us what type of assignment do we want in this case. Usually what we will do is, we will enter a constant value. We know the volume of the domain from our CAD. So we divide the total energy by the volume, and then we'll enter a watt per meter cube value. That's what we usually do, right? So what if we didn't have to know the volume of the particular zone in advance? What if we could use an expression to just simply assign the overall heat source and then divide it by the volume? So that's what I'm going to go ahead and do. I'm going to click on expression and say I want this zone to have an overall heat production of 20 watts. Okay. So what I'm going to go ahead and do is I'm going to put in 20 watts divided by the volume of this particular zone. So you can see that the name of the zone is heat zone. Okay. So what I'm telling in this expression for Fluent to do is divide 20 watts by the volume of this particular fluid domain. And I'm entering this expression directly in this field. Before I erase the other units that were by default present, you could see that Fluent was giving me a message invalid syntax or incomplete expression. That's because it was not complete. Once you have the correct complete expression in the field, it's not going to give you any more errors. So you can just simply go ahead and hit OK and then apply. Okay. All right. So we've done this portion here. Now, whatever other expressions we are going to write, we are going to use the expression editor. Before we do that, though, let me go ahead and convert my inlet to a velocity inlet. We'll come back to it later, and then let me assign my outlet as a pressure outlet. Okay, all right. So now we can get started with writing all our expressions in the expression editor. So this is the outline view, and this is where you can use or enter expressions in the editor. So just right click on it, go ahead and hit new. And this opens the expression editor box. Okay. So remember how I said that I want the pressure at the outlet to be a transient function? So I'm going to vary it with time. So let me just put this some name of the expression, right? So any name. This is just an assignment for the actual expression that you write so that you can select it from drop-down menu. So you could make it P outlet, you could make it P out, whatever you want. So this is the definition is where I write the expression. Now, say, for example, you're completely new to writing expressions. You don't know how to start. You can have some idea of how to use the functions and variables by looking at these drop-down menus over here. So I'm going to enter a conditional statement over here. So I could go to conditional and then I could click on if. And it gives me the overall syntax of an if statement, right? So there is the condition first, and then what happens if the condition is met, what happens if the condition is not met, okay? So if you are completely brand new to writing expressions, I would say use these drop-down menus quite often. So I'm gonna say that if my time is less than 0.5 seconds, and seconds will go in square brackets. Remember, the units go in square brackets. Then I want my pressure to be 0 Pascal. If not, then I want my pressure to be 100 Pascal. Okay. So what I've basically done is if time is less than 0.5 seconds, my gauge pressure at the outlet should be 0. If not, then it should be 100. Okay. So no more errors, no more messages. So this is okay. I'm going to go ahead and hit okay. I also get the mass flow rate at the outlet. So let me go ahead and enter another expression over here. And as soon as I click on M, it'll give me a bunch of options to choose from. Okay, so I could go with mass flow, or if I was writing some other kind of expression, maybe I'm going to use a reduction or an averaging function, then I could also go with mass flow average. But in this case, I'm simply going to choose mass flow. And then again, we are going to enter the location where I want the mass flow. So I want it at the outlet. Okay, I'm going to plot it later on when I run the simulation. All right. Now, another expression that I want to add is the pressure drop expression. That is quite common. We do it for internal flows all the time. The difference in static pressures between the outlet and the inlet, right? I don't want to do it manually. I don't want to, compute the outlet pressure and then the inlet pressure and then subtract it manually after my simulation is done. So what I do is I just put in pressure drop over here. And think about it the way you would go about manually extracting this information. What do? We take the mass flow average at the outlet of static pressure and mass flow average of static pressure at the inlet and then subtract, right? So we're going to do the same thing in the form of an expression. So we'll do static pressure at the outlet minus, let me go ahead and copy the same expression over here, Control C, Control V, and I'm just going to change the name from outlet to inlet. Now, the other thing that you may be interested in is, say, for example, you have a lot of flow boundaries in your problem, and you don't remember the name assignments of individual boundaries, right? In this particular case, I marked it as outlet and inlet. But what if you had a couple of different boundaries that you were working with and you don't remember the exact names that you assigned? You could also just look at locations, and you could look at particular cell zones or boundary zones. So now you know the exact name of the location that you want to compute your functions at. Okay, so this can be another good way of making sure that the name in between the quotes that matches with what you have assigned in your flow domain. Okay. All right. Okay, so time to enter the turbulent velocity profile at the inlet. There were two values that I was supposed to assign, the maximum velocity and the maximum radius. So let me quickly go ahead and assign those values. So this is just a variable that has an assignment of 0.5 meter per second. And another one for the maximum radius. I have this value known from my CAD geometry. What is the maximum radius at the inlet? So that is 0.005 meter. Okay. All right. And we calculate another expression, which is the radius of the inlet. Now, this is what makes it a multi-valued expression, because remember, at the inlet boundary consists of a face, okay? It consists of multiple faces from the mesh that is used to describe that particular boundary, okay? So at every face center, your coordinate is going to be different. Your coordinate of XYZ is going to be different. So how do you calculate the radius at any point? You use the same mathematical expression that you would when you're doing, hand calculations, right? So it's going to be x squared plus z squared whole square root, okay? So if you look here, the inlet, if I go ahead and display the inlet, it is assigned with the x and z axis, okay? So that's why when I write the expression for radius, I'm going to use those two coordinates to calculate the value. And then the square root of this entire function, okay? The same thing that we would do, when you're just calculating the radius of any circle, okay? So, all right. So once I have the individual components of the overall turbulent velocity profile ready, I can finally go ahead and build my velocity inlet. So the entire expression was Umax. And because we have already entered an expression in the name of Umax, when you type in U, there is an automatic suggestion of choosing one of the predefined expressions. Okay, so if you've already defined an expression, that also shows up as a suggestion. So you have Umax into 1 minus radius, something that we just defined, and max radius divided by max radius, 1 divided by 7. So this is the overall function that I wanted to assign at my velocity for assigning the turbulent velocity profile, okay? So 3 of these values, 3 of these variables in this expression, they are actually predefined expressions. So you can use multiple expressions to calculate derived variables. That's the beauty of using an expression manager, okay? All right. So I have 7 expressions defined over here. If you hover over these, right, they will give you some more information about what you've defined. They'll tell you whether it is single valued or whether it is constant valued. It'll also give you the dimension, the final SI dimension for the expression so that you know where all it can be assigned, okay? So now that we've defined all these expressions, let's actually go and assign it. We never did that. So we go to inlet velocity. Where you would put down the velocity magnitude, you instead click on the drop-down menu, and it shows you only those expressions. Fluent is very smart, right? So it shows you only those expressions that are dimensionally consistent with velocity. So we want to assign this function over here. And then I'll put some arbitrary number for temperature. And then at the outlet, instead of defining a constant value for gauge pressure, again, see, only the pressure expressions are shown in the drop-down menu. So I'm going to go ahead and use P outlet. Okay, excellent. So now that I've assigned all these values over here, let me use the expressions and report definitions, because we talked about how expressions can be used for post-processing as well. So say, for example, you wanted to plot an expression while your iterations are being solved. You can simply go to report definitions, right click, click on new, and then here you have something called expression. So let's go ahead and plot pressure at the outlet. because I want to see whether it varies with time as we intended. Okay, and let's print to console. This is going to report file, report plot, and it's going to print to console. And then we are also going to plot the pressure drop. Okay. Excellent. So I can then go ahead and initialize this guy. If it takes a lot of time, I also have a solved case ready. Actually, let me show you the solved case because the number of cores on my machine is limited and I have 2 Fluent sessions open. Okay. All right. So the hybrid initialization is done. Hopefully it doesn't take too much time. Let me just put this number of time steps just to 5. I had a Fluent session open for the very same reason. Sometimes when you have too many applications open on your machine, it's tend to freeze. Instead of waiting for that to compute, because I feel like I had 2 sessions open and one had more compute cores than the others. But okay. So in this particular case, I already solved the case and I want to show you some things in terms of post-processing. Okay. Remember, we had a velocity profile assigned at the inlet. So because we have a predefined expression in this particular setup, when you open contours after your simulation runs for a few iterations, you will automatically see an additional option of looking at the contours of expressions. Okay, so under expressions, if you look at the drop-down menu, there are only 2 expressions that had multi-valued solutions, right? So all other were single valued because there was just one constant return value. But for velocity inlet and radius inlet, because they were varying with the spatial coordinates, you can actually plot them on a field. So that's what we are going to do. We are going to look at the velocity at the inlet. And if you look here, instead of a constant value, say, for example, 5 meters per second or 6 meters per second, you actually see a variation from the perimeter of the inlet to the interior, depending on the radius that was calculated, okay? So this is what expressions can do in terms of giving you additional ability of manipulating your boundary conditions. The other thing that I also want to show you guys is that because we had the report definition for the pressure outlet, we can actually go ahead and look at the outlet plot of how the pressure varied. So say, for example, if I calculate this for another time step, you can see that the pressure varied based on the expression we assigned. So up till 5 seconds, it was supposed to be 0 gauge pressure at the outlet. And then after that, it was supposed to be 100 Pascal at the outlet, right? So right at the 5-second mark, you can see a jump. And that shows you how the pressure varied. And we were able to assign a transient value to this particular flow boundary. Similarly, you could also plot other things like pressure drop. I think in this particular simulation, I did not set up an additional expression for pressure drop. But if you wanted to see how it varied with different iterations, you could plot it in a similar fashion. All you would need to do is add another expression to your report definition. Okay. Now, this particular plot is visible if you add it to the report definition, but you could also just go to your expression editor and use this plot functionality sorry, closed it. But you could also just look at this value over here to see how your pressure is varying with time, because that's the expression that you've entered. So if you want to make sure that it has been assigned correctly, you could use either this or you could use the report definition. Okay, so whatever values you've computed, you can, come here and look at it. Now, remember, I told you that only single valued expressions can be calculated over here. So say, for example, your simulation has run for a few iterations, and now the data is associated with each and every cell. You can come to the expression editor and hit this green refresh button, and it'll give you the current value at this particular time step. So at this particular time step, your pressure drop between outlet and inlet is around 99 Pascal. So you run it for a few more iterations, few more time steps. This value may change depending on how the flow progresses. So all this extra capability is available to you through the expression editor. So make sure that you're able to use this for your own problems. Okay. So let me go back to my PowerPoint presentation so that I can just summarize everything that we learned today. So Fluent Expressions and the Expression Manager can be used to easily customize your case setup, especially if you have variable boundary conditions, cell zone conditions, material properties. You can do that without needing to use user-defined functions or any complex type of programming language. I also added some useful expressions in this summary slide. So these are the most frequently used expressions for medium range CFD simulations. So if you guys want to pause at this slide later on and use these expressions to build your own, feel free to do that. Okay, so with that, I'll conclude today's session. If you guys have any questions about the content that I covered today, feel free to leave it in the Q&A box and I'll be happy to answer. Someone thanked us for this session, so appreciate everybody's participation. Hopefully it was useful. But I'm going to wait a few more seconds here. If anybody has a question on how expressions can be used for their own problems, feel free to let us know. A full list of variables and all the mathematical, conditional, trigonometric functions that Fluent Expression language supports, everything is available in the Fluent User Guide. So if you go to the Fluent Expression language section, it lists all the different functions that you can use along with all the variables, all the units. So that should be a good starting point for you to be able to build your expressions as needed. Okay, I don't see any questions, so I'll go ahead and end the session for today. And if you guys have any feedback that you'd like to share with us on how we can make our content better, feel free to do that. All right. Okay, then. Excellent. Thank you, Saeed. Thank you for your feedback. Appreciate it. Thank you. All right, you guys have a good day and we'll see you next time. Bye-bye.